Hello and welcome to yet another video of Cornerstones of Math. In this video, I explain problems from 2023 entrance exam to Chennai Mathematical Institute, a distinguished higher education and research institute in India specializing in physics, math, and computer science. The Bachelor of Science or undergraduate entrance exam is divided into two parts. Part A consists of moderately difficult problems, and Part B consists of 6 very difficult problems and are only graded if students meet certain criteria in Part A. One of my viewers suggested that I should explain these 6 problems in Part B, and upon examination I found that the problems are both extremely difficult yet also quite interesting. So let's dive into those 6 problems from the entrance exam of year 2023. Here's the first problem, B1. We want to find odd integers n that is greater than 1 for which n is a factor of 2023 to the nth power minus 1. Problem A, find the two smallest such integers. Problem B, prove that there are infinitely many such integers. So problem A first, and we can just start testing with the smallest possible odd number, which is n equals 3. The question here is 2023 to the third power minus 1 divisible by 3? We start with the fact that 2023 is congruent to 1 modulo 3. Then we use some famous properties of modular arithmetic, especially the compatibility with exponentiation and multiplication. Using either of these properties, we can easily realize that 2023 cubed is congruent to 1 cubed. Hence 2023 cubed minus 1 is congruent to 0 mod 3. That is, n equals 3 works. Next, we move on to the next smallest odd number, 5, and check if 2023 to the 5th power minus 1 is divisible by 5. This time, we must use modulo 5 arithmetic. In this case, 2023 is congruent to 3 modulo 5. So 2023 to the 5th power is congruent to 3 to the 5th power, which is again congruent to 3 mod 5. Therefore, 2023 to the 5th power minus 1 is congruent to 2 modulo 5, which means that n equals 5 does not work. Moving on to n equals 7, now using mod 7 arithmetic, and 2023 is actually a multiple of 7, meaning that 2023 to the 7th power is also a multiple of 7, meaning that 2023 to the 7th power minus 1 is congruent to 6 modulo 7. Therefore, n equals 7 also does not work. Next, with n equals 9, first we have 2023 is congruent to 7 mod 9, and here we have to get to the 9th power, but even 7 to the 9th power is a pretty large number. So I prefer increasing the power 1 at a time, using the aforementioned compatibility with multiplication. That is, 2020 squared is congruent to 7 squared, which is congruent to 4 modulo 9. And for cubed, we use that squared is congruent to 4, and we need one more 2023, which is congruent to 7, hence congruent to 4 times 7. We can do this process on, and you can notice the periodicity here, 7, 4, 1, 7, 4, 1, and go on. So you can easily find that 2023 to the 9th power is congruent to 1 modulo 9, hence 2023 to the 9th power minus 1 is congruent to 0 modulo 9. Therefore, n equals 9 works. Therefore, two smallest valid integers are n equals 3 and 9. Problem B, proving that there are infinitely many such integers. We start from the result of the previous problem, which is that some of the smallest integers n satisfying the given condition are n equals 3, 9, and so on. From here, let's take a guess. If some positive integer k is a factor of 2023 to the kth power minus 1, then perhaps 3k is a factor of 2023 to the power of 3k minus 1. Let's prove this guess. If k is a factor of 2023 to the power of k minus 1, Then we have 2023 to the power of k is congruent to 1 modulo k. With this, if we examine 2023 to the power of 3k minus 1, we can factor this into 2023 to the power of k minus 1 times 2023 to the power of 2k plus 2023 to the power of k plus 1. Here, 2023 to the power of k minus 1 is congruent to 0 by our assumption, meaning that the first factor, 2023 to the power of k minus 1, is divisible by k. As for the second factor, we investigate by modulo 3, with knowledge of 2023 being congruent to 1 modulo 3. Then you can easily find out that 2023 to the power of 2k plus 2023 to the power of k plus 1 is congruent to 1 to the power of 2k plus 1 to the power of k plus 1, hence congruent to 0 modulo 3. That is, the second factor is divisible by 3. Therefore, 2023 to the power of 3k minus 1 has a factor 3k, which completes the proof of our guess. And by our guess and the previous result that n equals 3 works, we know that every power of 3 is also a valid exponent, meaning that there are infinitely many such integers n. Problem B2. Let z plus denote the set of positive integers. We want to find all functions g from z plus to z plus such that the following equation holds for any m and n in z plus. The equation is g of n plus m equals g of n plus nm times n plus m plus g of m. Prove that g of n must be of the form the summation of ci times n to the ith power, where I changes from 0 to d. That is, g of n is the polynomial of n. And find the precise necessary and sufficient conditions on degree d and on coefficients c0, c1, cd to satisfy the required equation. Well, finding the general expression right away is difficult, so we are going to test our given equation with some simple integers first to see if there's a noticeable pattern. First, if we try m equals 1 and n equals 1, the simplest case, we obtain g of 2 is equal to g of 1 plus 1 times 2 plus g of 1, which gives 2 times g of 1 plus 1 times 2. Next, let us fix the value of m as 1, but change the value of n to n equals 2. Then we obtain g of 3 equals g of 2 plus 2 times 3 plus g of 1, and using the previous result of g of 2, we obtain 3 times g of 1 plus 1 times 2 plus 2 times 3. And again, if we keep the value of m to 1 but increase n to n equals 3, we obtain g of 4 equals g of 3 plus 3 times 4 plus g of 1. And again, using the previous result for g of 3, we obtain 4 times g of 1 plus 1 times 2 plus 2 times 3 plus 3 times 4. Now, many of you might have spotted the pattern here, which allows us to infer the general expression. For all positive integers n, g of n must be n times g of 1 plus 1 times 2 plus 2 times 3 and so on until n minus 1 times n. Or using the sigma notation, n times g of 1 plus the summation of I times I plus 1, where I changes from 1 to n minus 1. Before we verify that this g of n satisfies the equation given in the problem, let us simplify this expression a little bit. We expand the expression inside the sigma, and we apply the following famous formulas for the sums of powers of consecutive natural numbers. These formulas are from I changing from 1 to n. If I increases up to n minus 1 instead, we have, for summation of I squared, we have n minus 1 times n times 2n minus 1 divided by 6, and for the summation of I, we obtain n minus 1 times n divided by 2. We can combine these two fractions using the common denominator 6, and this part is 2n plus 2, hence we can divide by 2 in both numerator and denominator, which gives the fraction n minus 1 times n plus 1 divided by 3, which can be written as n times g1 plus 1/3 times n cubed minus 1/3 times n. And if we rearrange this by decreasing order of n, we obtain 1/3 n cubed plus g of 1 minus 1/3 times n. You can notice that this is a cubic polynomial. Now let us verify that this expression for g of n indeed satisfies the equation given in the problem. For any positive integers m and n, using the obtained result, we have g of n plus m equals 1/3 times n plus m cubed plus g of 1 minus 1/3 times n plus m. Here, if we expand this part, we obtain this, and if we distribute like this, we obtain this part. Let us rearrange terms. So we first write 1/3 n cubed, then n term g of 1 minus 1/3 times n, and we can write this part as nm times n plus m, then m cubed term 1/3 m cubed, then m term g of 1 minus 1/3 times m. You can realize that this equals g of n plus nm times n plus m plus gm, which is this right-hand side. So our obtained expression indeed satisfies the given equation. In this expression, since there are no constraints on the value of g of 1 except that it must be a positive integer, we can write g of 1 as an arbitrary positive integer c, which gives g of n equals 1/3 n cubed plus c minus 1/3 times n. If we compare this expression with the sigma notation given in the problem, we can easily notice that the degree d is 3, and coefficients are c0 equals 0, c1 equals arbitrary positive integer c minus 1/3, c2 equals 0, and the leading coefficient c3 equals 1/3. Now problem B3. Suppose that for a given polynomial p of x, which is x to the power 4 plus ax cubed plus bx squared plus cx plus d, there is exactly one real number r such that p of r equals 0. First problem, if a, b, c, and d are rational, show that r must be rational. And problem b, if a, b, c, and d are integers, show that r must also be an integer. And possible hint, also consider the roots of the derivative p prime of x. Alright, so problem A first. We are given information about the number of real roots of p of x, but considering the possible graphs of a quartic function is a complicated process. Therefore, as the hint suggests, we will consider the roots of a derivative p prime of x first, which is a cubic function. More specifically, it is a cubic function with positive leading coefficient, hence the possible candidates for its graph are quite limited. So let's deal with the question, what are possible graphs of this cubic function p prime of x? Well, if you recall what you have learned in calculus courses, you can easily realize that these are possible graphs for the derivative p prime of x, which I categorized into 4 cases. The first case is typical increase, decrease, increase graph of a cubic function, which has 3 distinct real roots alpha, beta, and gamma. In the second case, the graph is still in increase, decrease, increase form, but now it meets the x-axis at only 2 different points, with either alpha or beta being a double root, the root with multiplicity 2. Here, only the case where alpha is double root is shown. In the third case, we have a different graph form, which occurs when alpha is a triple root, the root with multiplicity 3. The last case is where alpha is the only real root, but not a triple root like the previous case. This occurs when the graph of a cubic function strictly increases all the time like the red one, or like the green one, there exists a decreasing interval, but the graph meets the x-axis only at x equals alpha. In these cases, the cubic function p' of x has one real root alpha and other two roots that are complex conjugates of each other. So with graphs of the derivative being narrowed down, let us now think about the corresponding graphs of the original quartic function p of x with one additional condition. P of x must have exactly one real root r as given in the problem. Let's actually start from the last case. Whether the derivative is a red graph or a green graph, the quartic function p of x first decreases, then keeps increasing. The minimum occurs at x equals alpha, and if you want to have only one real root r, then this alpha must be the real root r. Notice that alpha, or r, is a double root of p of x because both the quartic function and its derivative become 0 at alpha. In a graphical sense, this alpha, or r, is a point where not only the value of the function, but also the slope becomes 0. Moving on to the third case, we also have a decreasing-increasing graph here, and the position for minimum, alpha, must be our only real root r. Here, alpha was already the triple root of the derivative p' of x, and now it must satisfy additional condition that p of alpha must be 0 as well. This is the case where alpha, or r, is a quadruple root, the root with multiplicity 4. In the second case, the slope becomes 0 at x equals alpha and x equals beta, but you can easily notice that in the case shown here, the minimum occurs at x equals beta. Therefore, if there's only one real root, then beta must be the real root r. This makes beta, or r, the double root of p of x. And finally, in the first case, we have a decrease-increase type of graph. In this case, the minimum can occur at x equals alpha or x equals gamma, depending on the position of the graph of the derivative. Here, I'm showing you the case where minimum occurs at x equals alpha. In this case, we can have exactly one real root if alpha is that real root r, making this alpha a double root. Alright, so now we have obtained every possible case for the graph of p of x having exactly one real root r. Now, can you identify the special characteristic of our real root r? Well, take a look at this. In any case, our only real root r is either a double root or a quadruple root. In other words, we have this important conclusion. The multiplicity of the real root r must be either 2 or 4. Let us deal with the multiplicity 4 case first. In this quadruple root case, p of x can be simply written as x minus r to the 4th power, which, if you expand using the binomial theorem, equals x to the 4th power minus 4rx cubed plus 6r squared x squared minus 4r cubed x plus r to the 4th power. It is also given in the problem that p of x is equal to x to the power 4 plus ax cubed plus bx squared plus cx plus d, with coefficients a, b, c, and d being rational numbers. Comparing the coefficients, minus 4r is equal to a, hence it is rational. This means that r is also rational, which concludes the proof for case 1. The second case, the case where the multiplicity is 2, deserves more careful consideration. R being the root of multiplicity 2 means that p of x contains x minus r squared as its factor, hence it can be written as x minus r squared times q1 of x, where q1 of x must be a quadratic function. Since r is a root with multiplicity 2, this q1 of x cannot have a factor x minus r. Moreover, since r is the only real root, the quadratic q1 of x must have complex conjugate roots. Moving on to the derivative, since r is also a root of the derivative, we can write p prime of x equals x minus r times q2 of x, where q2 of x is a quadratic function. Now the difference here is that q2 of x can have other real roots. However, those real roots are all different from r, and the graphs tell us that the multiplicity of root r in the derivative cannot exceed 1. Therefore, we can also say that there is no factor x minus r in q2 of x as well. So we found out that p of x contains two x minus r's in its factors, and p prime of x contains only one x minus r as its factor. What does this knowledge tell us? Well, this means that the greatest common divisor of p of x and p prime of x must be x minus r. However, this is not the only method to find the GCD. And since my viewers are clever, they might have remembered the famous Euclidean algorithm, which is a recursive method to find the greatest common divisor. Suppose that we want to find the GCD of two polynomials f of x and g of x. The basic mathematical principle of Euclidean algorithm, which will be stated here without the proof, is that if we divide f of x by g of x, suppose that we obtain quotient q of x and the remainder r of x. Then GCD between f of x and g of x is equal to the GCD between g of x and r of x. Based on this principle, we can come up with the following algorithm. First, we divide f of x by g of x, and we find the quotient q1 of x and the remainder r1 of x. Then the GCD between f of x and g of x is also the GCD between g of x and r1 of x. In order to find that GCD, we now divide g of x by r1 of x to obtain the quotient q2 of x and the remainder r2 of x. And then we do the same thing with r1 of x and r2 of x. So we divide r1 of x by r2 of x, obtain quotient q3 of x and the remainder r3 of x, and we go on and on. Here the algorithm terminates when the remainder becomes 0, like Rn of x equals 0 in this example. By the successive application of this principle, the GCD between f of x and g of x is equal to the GCD between Rn-2 of x and Rn-1 of x, which is Rn-1 of x if the remainder is 0. And this is how we find the GCD with Euclidean algorithm. Here it is given in the problem that p of x, and thus its derivative p prime of x, both have rational coefficients. If we attempt to find the GCD of p of x and p prime of x by Euclidean algorithm, we essentially calculate some remainders r1 of x, r2 of x, and so on. And since these remainders are calculated by simple arithmetic operations, all of these remainders also have rational coefficients. Since the GCD of p of x and p prime of x has to be one of these remainders, we also have the conclusion that such GCD also has rational coefficients. But we have already showed that such GCD is x minus r. Therefore, r, which appears at the 0th degree term of the GCD, must be rational, which concludes the proof for case 2 and thus concludes the entire proof. Now let's move on to problem B. If the coefficients a, b, c, and d are integers, then our only real root r also must be an integer. We will use the famous proof by contradiction, which obviously starts by assuming that our real root r is not an integer. The coefficients of polynomial p of x are rational numbers because they are integers. Therefore, by the result of problem A, we can still say that r is rational. Since r is a rational number that is not an integer, we can express r as m over n, where m and n are co-prime integers, and n is not equal to 0, and also not equal to 1 if r is not an integer. Since r is a root of p of x, we know that p of r, or p of m over n, equals 0. which can be expressed like this. And if we clear out the denominators by multiplying n to the fourth power, we obtain this equation. So we obtain this, and since n is not equal to 1, n must be a multiple of some prime factor p, hence we can write n equals some integer k times prime number p. Then, from equation 1, m to the fourth power can be expressed like this, basically n times something, and since n is a multiple of p, we know that m to the fourth power is also a multiple of prime number p. Now, what does this tell about m? Using the divisibility by p, m can be expressed as p times some integer l plus the remainder part s, which can have integer values from 0 to p minus 1. Then m to the fourth power can be expressed like this. We have p here, and since m to the fourth power is a multiple of p, this s to the fourth power is also a multiple of prime number p. Now, among the values that s to the fourth power can have, 1 to the fourth power, 2 to the fourth power, and p minus 1 to the fourth power cannot be a multiple of p since p is a prime number. Therefore, the only possible case is that s must be 0. This means that m is equal to l times p. Therefore, m and n are both multiples of p, which contradicts the condition that m and n are co-prime integers. Therefore, our real root r must be an integer, which concludes the proof. Problem B4 consists of two parts, problems A and B. There are n students in a class and no two of them have the same height. The students stand in a line, one behind another, in no particular order of their heights. Problem A. How many different orders are there in which the shortest student is not in the first position and the tallest student is not in the last position? And we'll move on to the problem B after we solve problem A. The first problem can be solved in two methods. We'll start with the first method, but before that, in this problem, I will refer to students as S1, S2, S3, Sn, whose heights are in an increasing order so that S1 is the shortest and Sn is the tallest. First, we just order all n students, and there are n factorial ways to do that. Then we have to exclude the cases where either S1 is in the front or Sn is in the last. As for the case where S1 is in the front, we just fix the position of S1 and order remaining n-1 students, which gives n-1 factorial ways. Similarly, as for the case where Sn is in the last position, we also have n-1 factorial ways. But we cannot simply subtract these two from n factorial to get an answer, because there is a duplicate case within these two. Namely, the case where S1 is in the front and Sn is in the last. Here, we fix positions of S1 and Sn, then order remaining n-2 students, which gives n-2 factorial ways. Therefore, the number of cases where S1 is in the front or Sn is in the last is n-1 factorial plus n-1 factorial minus n-2 factorial, and we have to subtract this number from n factorial, which easily simplifies to n-2 factorial times n squared minus 3n plus 3. In the second method, we start with only n-2 students without the shortest one S1 and the tallest one Sn. The number of ways to order the remaining n-2 students is n-2 factorial. Next, for each of these arrangements, we will insert the shortest student S1 between two students or in the either end. Notice that S1 cannot go to the front end, but they can go to the rear end. Hence, there are total n-2 spots that S1 can go. So we have n-2 ways to insert S1. Next, in this new arrangement, which includes S1, we insert the tallest student Sn. We currently have total n-1 students, and since Sn cannot go to the last place, but can go to the first place, there are total n-1 ways to insert Sn. But we are not done yet, since there is an additional case we haven't considered yet. In fact, S1 can go to the front in the first step only if the next person Sn also goes to the front, hence Sn is in front of S1. This particular arrangement hasn't been counted in previous cases, so we must include this case here. Therefore, we have n-2 factorial times n-2 n-1 plus the additional case 1, which simplifies to the same answer n-2 factorial times n squared minus 3n plus 3. Now let's move on to the much more difficult problem B. Let's read first. The badness of an ordering is the largest number k with following property. There is at least one student x such that there are k students taller than x standing ahead of x. The problem is to find a formula for gk of n, defined as number of orderings of n students with badness k. For example, the ordering 64, 61, 67, 63, 62, 66, and 65, where the numbers denote heights, has badness value of 3, as the student with height 62 has 3 taller students with heights 64, 67, and 63 standing ahead in the line, and nobody has more than 3 taller students standing ahead. So this is the concept of the badness. And here's a possible hint for problem B. It may be useful to first count orderings of badness 1 and /or to find fk of n, which is defined as the number of orderings of n students with badness less than or equal to k. Alright, as for this second problem, we will do exactly what the hint suggests. With the ordering of n students, first we will find g1 of n, the case where the badness is 1. Then we will find fk of n, which refers to the cases where the badness is less than or equal to k. And then finally we will find gk of n, where the badness is exactly k. So the first step, finding g1 of n, where the badness value is 1. We will search for the relation between g1 of n and g1 of n plus 1, and such relation will allow us to find a general expression for g1 of n. When we are considering the case with n plus 1 students, we can think of it as the union of the shortest student S1 and the remaining n students who are all taller than S1. This distinction will allow us to use g1 of n when finding g1 of n plus 1. So let's think about this. How can the badness of the ordering of these n plus 1 students becomes 1? And how can we make use of the case with n students when doing so? Well, think of constructing an ordering of n plus 1 students as inserting the student S1 to the already existing order of n students in one of the positions 1 to 3 and so on between students or at both ends. Then we can make the final badness become 1 as follows. The first case is when n students are forming an ordering with badness 1, and the student S1 goes to either positions 1 or 2. If you keep calm and think about it for a while, you can realize that when S1 goes to either positions 1 or 2, the badness remains 1. But when S1 goes to position 3, then the badness increases to 2, because then 2 people taller than S1 will be standing in front of S1. So there are only 2 valid positions. Hence, there are 2 times g1 of n ways to form an ordering of length n plus 1 with badness 1. Actually, there is another way though. In the second case, n students are forming an ordering with badness 0. This is only possible when they are arranged in an increasing order. If we insert S1 to position 2, then the final ordering will have the badness value of 1. So there is only one way for case 2. N students are arranged in an increasing order, and S1 goes to position 2. Combining these two results, we can find out the relation between g1 of n and g1 of n plus 1, which is g1 of n plus 1 is equal to 2 times g1 of n plus 1 for all natural numbers n. With this relation and the initial value, which is the g1 of 1 equals 0, it's pretty obvious if you think about it, we can find the general expression for g1 of n. This is a really simple recurrence relation, so you can just calculate the first few terms and then take a guess. Or if you want to do it in a more formal way, you can rearrange terms into g1 of n plus 1 is equal to 2 times g1 of n plus 1. So we have the same form here, and here 2 is multiplied. Therefore, sequence g1 of n plus 1 is a geometric progression. The common ratio is 2, and the first term is g1 of 1 plus 1, which is 1. Therefore, the general term for the sequence g1 of n plus 1 is first term 1 times the common ratio 2 to the power of n minus 1. This gives g1 of n equals 2 to the power of n minus 1 minus 1. Let's move on to step 2, which is to find fk of n, where the badness value is less than or equal to k. The previous step for badness 1 does not directly help us here, but at least we can borrow the idea and apply it here as well. That is, let us try to find the relation between fk of n and fk of n plus 1. So we try to deal with n plus 1 students by dividing them into the shortest student and the remaining n students, who are now ordered so that the badness is less than or equal to k. There are fk of n ways to do so. We want to insert the shortest student S1 to this ordering of n students in a way that the final badness is still less than or equal to k. So what positions can S1 go into? Well, S1 can go into positions 1, 2, 3, so on up to k plus 1, right? If S1 goes to k plus 1, there will be k people in front of S1, but if S1 goes to the position k plus 2, then there will be k plus 1 people in front of S1, increasing the badness to k plus 1. Since there are total k plus 1 positions that S1 can go into, fk of n plus 1 has to be expressed as k plus 1 times fk of n. Are you sure? Well, in order for this relation to work, there must exist at least k plus 1 positions in the first place. That is, this reasoning works only if n is greater than or equal to k, or our desired badness value k is less than or equal to the total number of students n. However, fk of n can still be defined even if n is less than k. The setting is the same. N students are ordered in a way that the initial badness is less than or equal to k, and we want to insert the shortest student S1. We have n plus 1 positions in total, which is also the same as the previous case. But the difference here is k is greater than or equal to the total number of positions n plus 1, meaning that even if we place S1 at the last position n plus 1, there will be only n people in front of S1, and since n is less than k, the badness value still remains less than or equal to k. Therefore, in this case, S1 can go to all available positions 1 to 3 ... n plus 1, and this changes the relation into fk of n plus 1 is equal to now n plus 1 times fk of n. And this second case is actually easier to deal with because the inner part of the function can decrease without any limitation. According to the relation, the general term fk of n is equal to n times fk of n minus 1. And here we can change fk of n minus 1 into n minus 1 times fk of n minus 2. And we can change fk of n minus 2 into n minus 2 times fk of n minus 3. And if we go on and on, we eventually arrive at n factorial times fk of 1, which is simply n factorial. And back to case 1, where n is greater than or equal to k. Like I said, this first case is actually a bit trickier. The beginning is simple. Now k plus 1 is being multiplied, so we have the general term fk of n equals k plus 1 times fk of n minus 1. And applying the relation again, k plus 1 is keep being multiplied, so we have k plus 1 squared fk of n minus 2, which equals k plus 1 cubed times fk of n minus 3, and so on. The problem here is we cannot go on like this forever, because now we have a limitation that the inner part of the function, which is n, cannot be less than k. Therefore, we can only go until fk of k appears, at which point the prefactor becomes k plus 1 to the power of n minus k. If we try to apply the case 1 relation again, this means that now the n plus 1 in this relation equals k, meaning that n equals k minus 1, which is less than k. Therefore, we cannot apply case 1 relation anymore, and we must apply case 2 relation from now on. Notice that case 2 relation is applicable when n plus 1 equals k, hence n equals k minus 1. Therefore, applying case 2 relation gives, now fk of k becomes k times fk of k minus 1. And if we do this on and on, we know where it arrives. As already shown in case 2, it will give k factorial. So we obtain this result from case 1. Therefore, from cases 1 and 2, we obtain this general result for fk of n. Here I also included the equality sign for case 2 as well, which you can easily verify by yourself. And finally, the last step, finding gk of n where the badness value is exactly k. This is really easy because gk of n can be obtained by fk of n, the number of cases where the badness is less than or equal to k, minus fk minus 1 of n, the number of cases where the badness is less than or equal to k minus 1. We have done case divisions for fk of n, so I will do case division here as well. For n less than or equal to k case, gk of n simply becomes 0. This makes sense, even though n less than or equal to k is kind of an impractical case. For more practical n greater than or equal to k case, now we have to do the subtraction k factorial times k plus 1 to the power of n minus k minus k minus 1 factorial times k to the power of n minus k plus 1. This k to the power of n minus k plus 1 is equal to k to the power of n minus k times k. And if we combine this k with k minus 1 factorial, it gives k factorial. So we can write the second term as k factorial times k to the power of n minus k. So we can group them with common factor k factorial, which is now multiplied by k plus 1 to the power of n minus k minus k to the power of n minus k. Therefore, we can express the combined result like this. The formula we obtained in step 1 is the special case of this where k is equal to 1. You can check it for yourself. As for this video, this is the end of problem B4. Problem B5. Throughout this question, every mentioned function is required to be a differentiable function from R to R, where R is the set of real numbers. The circle symbol denotes composition of functions. We have 3 problems A, B, and C, and let's take a look at problem A first. Suppose that f of f equals f. Then for each x, one must have f prime of f equals blank or f prime of f of x equals blank. Complete the sentence and justify. Alright, so we are given the condition f of x equals f of x. If we differentiate both sides, then we obtain f prime of f of x times f prime of x equals f prime of x, which can be rearranged into f prime of x multiplied by f prime of f of x minus 1 equals 0. Hence, we have f prime of x equals 0 or f prime of f of x equals 1. Moving on to problem B. For a non-constant f satisfying f of f equals f, it is known and you may assume that the range of f must have one of the following forms: the entire set of real numbers, from negative infinity to b, from a to positive infinity, or from a to b. Show that in fact the range must be all of set R and deduce that there is a unique such function f. And we have hint. For each y in the range of f, what can you say about the value f of y? Also, if the range has a maximum element b, what can you say about the derivative of f? Alright, first, we have the same condition as given in the previous problem. Therefore, by the result of problem A, f prime of x equals 0 or f prime of f of x equals 1. It is stated in the problem that f is a non-constant function, hence the derivative cannot be always 0. Therefore, the other condition is true, which is that f prime of f of x equals 1. Now let's deal with the first part of the hint. For each y in the range of f, which can be also expressed as f of x since it is in the range of f, if we investigate f of y, it is equal to f of x, and by the given condition, this equals f of x, which is just y. This means that f is an identity function on the range. And this is a nice time to state our end goal. If we can show that the range is indeed all of the set of real numbers, then we can conclude that the unique function we want to find is an identity function f of x equals x for all real numbers x. So let's show that the range is the entire set of real numbers. For now, all we know is what was given in the problem, that the range is one of the 4 intervals, the entire R from negative infinity to b, from a to infinity, or from a to b. The gist here is that if the range has a finite endpoint such as a or b, then that finite endpoint must also belong to the range. We will also use the second part of the hint. If the range has a maximum element b, like this, what can you say about the derivative? Here, it is sufficient to show that if we assume that the range has a maximum element b, then we arrive at contradiction. The other 2 cases with minimum element a is just symmetric to this case, hence invalidating this range will ensure that the range is the entire set of real numbers. So let's assume that our range has a maximum value b, and let's recall the result we just obtained. For each y in the range of f, f of y equals y. This means that the derivative f prime of y is equal to 1 for all y in the range except the endpoint b. So what about at the endpoint b? Well, since f is differentiable, we can use the one-sided limit for the derivative at the endpoint. That is, the derivative f prime of b is given as f of b plus h minus f of b divided by h, where h approaches 0 from the left. Since h is negative here, b plus h is in our range, hence we can use the identity function for f of b plus h. This gives f of b plus h equals just b plus h, and since f of b equals b, we just obtain the value 1 for f prime of b. However, there is another way to calculate the derivative, using that b, f of b is a maximum point. I wrote local maximum point here because this property works for local maximum points as well, and this is actually the very famous property that you may have learned in your basic calculus course. For small h, which can be either positive or negative, f of b plus h is less than or equal to f of b because f of b is the maximum value. This gives f of b plus h minus f of b less than or equal to 0. Hence, if you divide by h and take the limit where h approaches 0, when h is positive, the direction of the inequality doesn't change, so we have the limit value that is less than or equal to 0. And when h is negative, the direction of the inequality sign changes, so now we have greater than or equal to 0. Since f is differentiable, these two one-sided limits are equal. Hence, the limit where h approaches 0 is 0, meaning that f prime of b is 0, which is the very basic and famous property that the differentiable function has 0 derivative at a local maximum point. So we obtained f prime of b equals 1 when we used the identity function property of f, and we obtained f prime of b equals 0 when we used the property of a maximum point. Obviously, this is a contradiction. Therefore, the range of f is the entire set of real numbers, and function f from R to R is uniquely defined as the identity function f of x equals x. A quick side note here, which you can skip because it is not part of the solution to the problem. In the previous problem, it is given without proof that the range of function f satisfying the given conditions can be only one of these four. Entire set of real numbers, from negative infinity to b, from a to infinity, or from a to b. These intervals may not seem very special, but they are in fact special in the sense that certain types of intervals are invalid for the range of f. First, the range cannot contain isolated points. That is, the range always has to be an interval. Second, the range cannot contain finite open endpoints, such as the open interval a, b, where a and b are finite. So, can we prove this? Yes, we can, and I will show the proof here. By the way, we will use the previously obtained following property in the proof. If y belongs to the range of f, then f of y is an identity function, f of y equals y. So let's start the proof. We will start from the fact that the given function f is a non-constant function. Therefore, there exists f of p and f of q in the range such that two values are different, or should I say, f of p is less than f of q. Next, we know that f is continuous since it is differentiable. This allows us to use the famous intermediate value theorem. That is, for every r that is in between f of p and f of q, we can always find c between p and q such that f of c is equal to r. In other words, every r between f of p and f of q also belongs to the range. This result alone already poses a significant restriction on our range, which is that only a single interval is suitable for our range. For example, the range cannot be isolated points like this, because if we pick f of p and f of q like this, then all values between these two must also belong to the range, And the range also cannot be disconnected intervals like this, because if we pick f of p and f of q like this, then all values between these two must also belong to the range. Therefore, the only possible range is a single interval like this. If we investigate all possible single intervals, we can find the following 9 different types of intervals, where a and b are finite numbers, and the last one, from negative infinity to positive infinity, is just the entire set of real numbers. Out of these 9 intervals, we want to show that first 5 are impossible to be the range of our function f. These are the intervals containing finite open endpoints. This leaves letter 4 as the only possible intervals, which contain closed endpoints if such endpoint is finite. In order to prove this, all we need to do is to show that if an endpoint is finite, then it must belong to the range. And let us only prove this for the lower endpoint a, since the upper endpoint case is just symmetric. So a is the lower endpoint of the range. And here's the previously obtained identity function property. Now, for a sufficiently small positive number h, a plus h lies within the range, since the range is an interval. This means that we can apply the identity function property to realize that f of a plus h is equal to just a plus h. Also, f is continuous. This means that the value of f of a is equal to the limit of f of a plus h when h approaches 0 from the right. Using the identity function relation, we have the limit of just a plus h, which gives a. So since a is equal to f of a and f of a belongs to the range, we know that a belongs to the range. Therefore, open endpoint with a is impossible. Only closed endpoint is possible with a. And this concludes the proof. Now let's move on to the remaining problem C. Suppose that g of g equals g and that g of g is a non-constant function. Show that g must be onto, g must be strictly increasing or strictly decreasing, and that there is a unique such increasing g. Alright, we start from the given condition g of g equals g. If we apply g once more, we obtain g of g equals g of g. Now, you may have learned this in pre-calculus course, which is that function composition operation is associative. Therefore, we can group the functions like this. And this is exactly the same condition as given in the problem B, now with g of g instead of f. Therefore, by the result of the problem B, this g of x, which can be also written like this, is an identity function x. This means that the inverse of g is g itself. Since the inverse of g exists, our function g must be onto, sometimes called surjective, and one-to-one, sometimes called injective. There are other terminologies to refer to this type of functions, such as g is one-to-one correspondence, or g is bijective. So we have proved the onto part, and since g is one-to-one and continuous, g must be strictly increasing or strictly decreasing. So we have already solved many parts of the problem, and only one more question left. Can we find such unique function g that is increasing? As for this question, let us actually take a wild guess. Which strictly increasing function would satisfy the property that the function is an inverse of itself? Well, it seems like only g of x equals x would satisfy such conditions. Therefore, let us guess that g of x equals x and try to prove this guess. In order to do so, we will show that if we assume g of x is greater than x or g of x is less than x, we reach contradiction. First, if g of x is greater than x for some x, then since g of x is a strictly increasing function, applying g onto this inequality preserves the direction of the inequality, hence we obtain g of x is greater than g of x. We have already shown that g of x is an identity function, hence the inequality becomes x is greater than g of x, which is a contradiction. Similarly, if g of x is less than x for some x, then since g of x is a strictly increasing function, applying g again doesn't change the direction of the inequality, hence g of x is less than g of x. And since g of x equals x, we have x is less than g of x, which is a contradiction. Therefore, g of x equals x, which proves our guess and hence concludes this problem. And the final problem, B6. Starting with any given positive integer a that is greater than 1, the following game is played. If a is a perfect square, take its square root. Otherwise, take a plus 3. Repeat the procedure with the new positive integer. The resulting set of numbers is called the trajectory of a. For example, the set 369 is a trajectory. It is the trajectory of each of its numbers. And here's the question, which numbers have a finite trajectory? And there's a hint. And if you wish, you can get partial credit by solving the following simpler questions. A. Show that there is no trajectory of cardinality 1 or 2. B. Show that the set 369 is the only trajectory of cardinality 3. C. Show that for any integer k greater than or equal to 3, there is a trajectory of cardinality k. And D. Find an infinite trajectory. Let's do the partial credit problems first, and then I will solve the main problem. So problem A. Show that there is no trajectory of cardinality 1 or 2. Let's use S to denote a trajectory. First, cardinality of 1. This means that S has only one element, A. This means that if we apply either square root or adding 3, it must give A as well. So we have either A equals square root of A or A equals A plus 3, which is impossible since A is an integer greater than 1. Next, the cardinality of 2. This time, set S can have two elements, A and B, where B is the greater number. We have a square root operation which decreases the number, and we have add 3 operation which increases the number. Therefore, A can be obtained by applying square roots to B, and B can be obtained by adding 3 to A. And since B equals A squared, the second relation becomes A squared minus A minus 3 equals 0. However, this equation does not give an integer root, meaning that this case is also impossible. Therefore, there is no trajectory with cardinality 1 or 2. Problem B, showing that 369 is the only trajectory of cardinality 3. The trajectory with cardinality 3 can be expressed as the set with elements A, B, and C, where A is the smallest number and the C is the largest number. We can increase the number by only adding 3, hence B must be A plus 3 and C must be B plus 3, hence A plus 6. Therefore, our set S has 3 elements A, A plus 3, and A plus 6. Next, the larger numbers must revert back to smaller numbers by taking square root. Therefore, we have 3 possibilities. A is equal to square root of A plus 3, A is equal to square root of A plus 6, A plus 3 is equal to square root of A plus 6. If A is equal to square root of A plus 3, squaring both sides and rearranging gives A squared minus A minus 3 equals 0. This equation does not give an integer root, hence this case is impossible. If A is equal to square root of A plus 6, Squaring both sides and rearranging gives a squared minus a minus 6 equals 0. This equation gives positive integer root a equals 3, which is a valid root. This value of a gives the trajectory 3, 6, 9. If a plus 3 is equal to square root of a plus 6, squaring both sides and rearranging gives a squared plus 5a plus 3 equals 0. This equation does not give an integer root, hence this is another impossible case. Therefore, set 3, 6, 9 is the only trajectory of cardinality 3. Problem C. Show that for any integer k greater than or equal to 3, there is a trajectory of cardinality k. We are going to use previously obtained trajectory 3, 6, 9 as a starting point. This is a trajectory with cardinality 3, and it is a trajectory of either 3, 6, or 9. This particular set has a looping property, i.e. the numbers cycle among these three in the order 3 becomes 6, 6 becomes 9, and 9 becomes 3, and 3, 6, 9, 3, 6, 9, and so on. From here, we can add numbers to the trajectory in the following way. As for 6, notice that 6 can be obtained by taking square root on 6 squared, and this 6 squared can be obtained by taking square root on 6 to the 4th power, which can be obtained by taking square root on 6 to the 8th power, and so on. Similarly, 9 can be obtained by taking square root on 9 squared, which can be obtained by taking square root on 9 to the 4th power, which can be obtained by taking square root on 9 to the 8th power, and so on. Therefore, we can obtain trajectory with cardinality k greater than 3 by adding 6 squared, 6 to the 4th power, 6 to the 8th power, and so on, or 9 squared, 9 to the 4th power, 9 to the 8th power, so on, to our starting trajectory 3, 6, 9, and starting from the largest number. For example, if we start from 6 squared or 9 squared, we obtain a trajectory with cardinality 4, and if we start from 6 to the 4th power or 9 to the 4th power, we obtain a trajectory with cardinality 5. In problem D, find an infinite trajectory. The intuition for this problem comes from the rule of this game, which is that we increase the number by 3 if it is not a perfect square. That is, if we obtain new numbers by keep adding 3's, then all of the obtained numbers have the same remainder when divided by 3. However, there exists a rule which stops the numbers from increasing. If a number becomes a perfect square, then we must take a square root of that number. So, is there a way to avoid this square root rule? Now, since we are dealing with adding 3, let us categorize the integers by remainders when divided by 3. That is, 3k, 3k plus 1, and 3k plus 2 when k is an integer. If we calculate the squares of them, we can realize that the remainder when these squares are divided by 3 is either 0 or 1, but it cannot be 2. That is, the square of any integer is of the form 3k or 3k plus 1. In other words, any integer of the form 3k plus 2 cannot be the perfect square. Therefore, when constructing a trajectory with this number, we must add 3, which results in another 3k plus 2 type integer, and we can go on with this adding process indefinitely. Therefore, we can conclude that any trajectory containing an integer of the form 3k plus 2 is infinite. Now let us solve the main problem, which is finding the numbers that give finite trajectories. We are going to use the hint, which says find a set with element n, where n is the smallest number in some trajectory S. So let n denotes the smallest number in a trajectory, and let us find the possible values of n. The first thing to notice is that n cannot be the perfect square, since it is the smallest number in a trajectory. Therefore, we can find a positive integer m such that n is greater than m squared but less than m plus 1 squared. Since n is not a perfect square, we must keep adding 3 until a perfect square occurs. Remember, it is possible that perfect square never occurs, which is the case when n is of the form 3k plus 2. Still, if the perfect square does occur, how can we relate that perfect square with our newly introduced variable m, the positive integer that makes n sandwiched between m squared and m plus 1 squared? Well, if you want to investigate every possible case, it is convenient if we construct this table, which I call mod 3 table. That is, the values listed in the table represent the remainders when divided by 3. We have n column here with remainders 0, 1, and 2, and for each case, we divide cases further by m, which can also have remainder 0, 1, and 2. It is worth mentioning that m is determined by n, so once we picked the value for n, the appropriate value of m is automatically determined. For example, if we picked n equals 7, which is a 3k plus 1 type number, then since 7 is sandwiched between 2 squared and 3 squared, the value of m is 2, which is a 3k plus 2 type number. Moving on, we have columns labeled m plus 1 squared, m plus 2 squared, and m plus 3 squared. Initially, n is less than m plus 1 squared, so if we keep adding 3's to n, it will arrive or go past these numbers. And using the remainders for m, we can calculate the remainders when these squares are divided by 3. Notice that the remainders is either 0 or 1, which coincides with what I have explained in the previous problem. A square of any integer can only give the remainder 0 or 1 when divided by 3. For now, only 1/3 of the table is filled for the case where n has a form 3k. We will fill the remaining part of the table when we deal with those cases. For now, let us focus on n equals 3k case. This remainder 0 does not change if we add a bunch of 3's to n. Therefore, if the growing number becomes the perfect square, that perfect square also must give the remainder 0. And that is what highlighted cells mean. If m is also in 3k form, then the first square that is also a multiple of 3 is m plus 3 squared, meaning that m plus 3 squared is the number that n can become by keep adding up 3's. If m is in 3k plus 1 form, then the first multiple of 3 occurs at m plus 2 squared, meaning that n will become the perfect square m plus 2 squared in this case. And similarly, if m is in 3k plus 2 form, then n will become the perfect square m plus 1 squared by adding 3's to it. So now you must have understood what this table means. So now let's move on to the next part of the table, the case where n is equal to 3k plus 1. You can fill out the remainder table for each case of m. Notice that the remainders are arranged in the same manner as the upper 1/3 of the table, because they are only determined by the remainder of m, which are arranged in the same manner. However, the highlighted cells in this case will be different. Now, n gives the remainder 1, which does not change if we add 3's. Therefore, in the table, now we must find the cases where the remainder 1 occurs for the first time, which are these cases. Remember the n equals 7 example that I gave you? 7 is in 3k plus 1 form, and since 7 is in between 2 squared and 3 squared, it means m equals 2, which is in 3k plus 2 form. According to the table, n will become the perfect square m plus 2 squared, which in this case 2 plus 2 squared, hence 16. And if you add 3's to 7, you'll realize that the number indeed becomes the perfect square at 16. And finally, the case where n equals 3k plus 2. But the thing is, we don't even need to investigate this case at all. You see, the remainder of the perfect square when divided by 3 can be only 0 or 1, meaning that n in 3k plus 2 form can never become a perfect square by adding 3's. So we have done some tedious works to fill, investigate, and highlight the table, but what for? Well, based on our investigation, we can make this important observation. If n can become the perfect square, which is possible when n is not in 3k plus 2 form, then that perfect square cannot exceed n plus 3 squared. Let me state again. The perfect square that n becomes cannot exceed n plus 3 squared, which then must become n plus 3 by taking square root. Since n is the smallest number in trajectory s, this n plus 3 must be greater than or equal to n. Since n is greater than m squared, we obtain this inequality, which implies that m squared is less than n plus 3, and the only positive integers satisfying this relation is 1 or 2. Now, if we investigate each value of m using this inequality, we can find appropriate values for n, which is n must be either 2, 3, 4, or 5. Among these four values, 2 and 5 are invalid because they are of the form 3k plus 2, which gives infinite trajectory. Moreover, n equals 4 is also an invalid case because 4 is a perfect square, hence it can become even smaller number, which is 2. Therefore, n equals 3 is the only possible value for the smallest number in a finite trajectory. So our finite trajectory S contains the smallest number 3 and the starting number A, which may or may not equal to 3. And we have to find which starting number A gives this finite trajectory. If we think of a process that starts from A and ends at the smallest number 3, it consists of a bunch of taking square root and adding 3 steps. By the way, after the number becomes the smallest number 3, it cycles through only finite set of numbers, namely 369, 369, and so on, which does not violate the finiteness of the trajectory, so we don't need to care about what happens after reaching 3. What I would like to do is to construct a reverse process which starts from 3 and ends at the starting number A. We can easily notice that this reverse process consists of squaring the previous number and subtracting 3 from the previous number. Here, notice that squaring a number and subtracting 3 from a number both preserve the prime factor 3 in a number. That is, we can realize that every number in a trajectory S is a multiple of 3. In fact, if we think about it, we can also realize that starting from 3, we can generate any multiple of 3 by the combination of these squaring and subtracting 3 steps. This means that any multiples of 3 can be the starting number A. Therefore, we have the conclusion that all multiples of 3, that is, the starting number A in a 3k form, have finite trajectories. And with this, we are done with problem B6. Hence, we are done with every problem in Part B of the Chennai Mathematical Institute's Bachelor of Science entrance exam of the year 2023. Thank you all for watching. Please hit that like button if you enjoyed this video, and I will see you in another video.